So yeah, here's the left-hand sum. Blah, blah, blah. So things that you want to notice is that the only difference between the right-hand sum with n equals 8 and the left-hand sum with n equals 8 is that the right-hand sum has the i's going 1 through 8, and the left-hand sum has the i's going 0 through 7. But it's the same number of rectangles. And so all these numbers in this block right here, I did not have to calculate them because I already knew them from here because they are the same as these numbers. And in fact, the only difference between the two sums is that the right-hand sum has this the a sub 8 and no a sub 0, whereas the left-hand sum has a sub 0 and no a sub 8. So in fact, I could get, once I calculate the right-hand sum, I can get the left-hand sum just by saying, I'm going to take the right-hand sum, I'm going to subtract off a sub 8 and add on a sub 0, which since a sub 0 was 0 anyway, all I really have to do is subtract a sub 8, and a sub 8 was 1. So all I have to do is take this number 3 3/16 and subtract 1, and I get 2 3/16. And that's what the left-hand sum is. But I've written everything out anyway, just to show where numbers are really coming from. So here's, all the calculation. I'm saying that the area is approximately equal to the sum from I equals 0 to 7 this time of a sub I. So that's sum for I equals 0 to 7 of f of x sub I delta x. Again, the expression that we want to keep our eye on because this is going to be key to what's coming. That got 2 3/16. So for this function, really because it's an increasing function, the left-hand sum is an underestimate, and the right-hand sum is an overestimate. And I know the area I'm looking for is between 2 3/16 and 3 3/16. Now, I could continue this process taking more and more rectangles. The delta x getting smaller and smaller. In fact, the delta x approaching 0. The number of rectangles approaching infinity. And that's how I could get these areas to be exact. But we're not there yet. We're not ready to go there yet. That's where we're headed. So for now, I just want to do one more quick example. Estimate the area under y equals ln of x. I'm going to demonstrate some calculator techniques here too. Y equals ln x over 1 to e using 4 rectangles in a right-hand sum. Does the estimate overestimate or underestimate the true area, which is a popular AP exam question? Does it overestimate or underestimate? And they'll usually be looking for a reason for why you think it overestimates or underestimates. All right, so what I will do is set up my chart. So I like to set up the chart. Look, people have different ways of doing it. I have I, x sub I, f of x sub I, delta x, and a sub I. Actually, a lot of times, if I only have 4 rectangles, I won't do the chart. I'll do it right on I'll draw the rectangles. Sometimes for me, that's easier. But I'll stick with the chart since I just showed you that. And I think especially for these weird numbers, it's going to be pretty useful. So my i's are going to be, since I'm using a right-hand sum and it's 4 rectangles, my i's are going to be 1, 2, 3, 4. But what the heck are the x sub i's going to be? And what is the delta x going to be? Well, here's where we can take advantage of what our discussion before when we realized that delta x is always the length of the interval divided by the number of rectangles, which really should be just sort of common sense or logic there. All right, so that means my interval is from 1 to e. So this is a and this is b. So my b minus a is e minus 1 over my n, which is the 4 rectangles. It's e minus 1 over 4. All right. Now, because I'm going to have a lot of weird numbers here, and then I'm going to have to take the ln of them all, because the function is y equals ln of x. All right. I'm going to have to go to decimal land here. I can't do this with fractions because, these are all going to be irrational numbers. All right, so here's how I'm going to get my x sub i's. So I don't even know what the first x sub I is, right? Because if I try to break this into 4 pieces, here's my x sub 1. What the heck number is that? All right, well, what it is since the width is always delta x, I can think about starting at 1 and adding delta x every time. All right, so my delta x is e minus 1 over 4. So let's put that into our calculator and see what it is. E to the 1, there's probably different ways to do that, but I did it like that, e minus 1, and then divided by 4. So I get 0.429 0.57. So I'm going to go ahead and write for my delta x as 0.430 because I'm rounding that to 3 decimal places. That's what my delta x's are. All right, now, here's a useful technique. We're going to have to use this delta x a lot. We're going to have to multiply it. We're going to have to add it. We're going to have to do all kinds of things, right? So one thing we can do with that number is we can store it in a variable. So we can take this number 0.429 and use the STO for store. Now you can store it in any alphanumeric variable, but since we're only using one, use the most accessible one, which is the x. So the x that you hit here, that's a variable. You can store numbers into it, right? So now if I do, 1 times x, it gives me that number. If I do 2 times x, it gives me twice that number. It has stored the value of 0.4297 with all its decimals into the variable x, and now I can use that. All right, so my x sub I is going to be 1 plus delta x. So all I have to do is go 1 plus x, which is really delta x, and I get 1.430, which I could have guessed that 1 plus 0.430 would be 1.430. But see, now I can just keep going plus x, and I get 1.859. 1.859, and then I'm going to go plus x again, remembering the variable I have stored as x is really delta x, so now I have 2.289, and then one more time, oh, I didn't intend to do that, but that's cool. All I did was hit enter, and it just repeated the same pattern. Cool. Now I get 2.718. That number should look familiar to you, because that number is e. That makes sense because x sub 4 is equal to e. All right, so that's going to be but I'll go ahead and put 2.718 there, even though it's really e. Okay, now I have to get f of all those numbers. So I need f of my 1.430 number. So my f of x is ln x. So I'll do ln of, ln of my 1.430 number is up here. So see how I'm always copying from the calculator so I don't have to write out the decimals and I don't get compounded rounding errors. So that one's 0.357. And then I have to do f of the 1.859. So ln of the 1.859 number is here. And that gives me 0.620. 0.620. All right, and then I have to do ln of the 2.289 number, which is here, and that is 0.828, 0.828, and I could continue habitually, but if I think about it, this number is e, and the ln of e is 1. All right, now I have to multiply across, so I know this one's going to be 0.430. This one, I have to do 0.357 times my delta x. So I go up and get my 0.357 number, and then because I stored the delta x in my variable x, I just go times x, and I get 0.154. So this one, I'm going to do my 0.620 number. So see how I don't have to enter any of these numbers, and I'm taking advantage of the fact that I stored delta x in the variable x. Now I got 0.266, and then my last number, I have to go the 0.828 times that number. So the 0.28 times x gives me 0.356, 0.356. And now I've filled out my chart. And now I can say that the area is approximately equal to the sum from I equals 1 to 4 of a sub I, and that equals, now I can just add these up. So I need to go, see, where does it start? The first number is the 0.154. All right, so the 0.154 plus the 0.266 number is here, plus the 0.356 number, which is here, plus the 0.430 number, which was my delta x, because it's just 1 times delta x. So I can just say plus x. And I get 1.205. That's my right-hand sum estimate. Now, let's think about whether it's an overestimate or an underestimate. So because I'm using right-hand rectangles, they touch the function on the right-hand side. So that means that the areas of the rectangles are always going to be outside the function. But why does that happen? It happens because this function is increasing. You know, if I had a function that was decreasing and I did right-hand intervals, I would get an underestimate. So because we're using a right-hand estimate on an increasing function, this is an overestimate. Okay, so the sum overestimates because a right-hand sum is used on an increasing function. And that's the justification you would use for why you know it's an overestimate. All right, now, with a discussion that we have so far about right-hand and left-hand sums, you are already prepared to do the worksheet called Riemann sums number 1. That's your first homework on this. And I'm still deciding whether we're going to keep in the same day the trapezoid and midpoint approximations, or if I'm going to save that for another lecture. To be announced.